And for our third talk, Marco will tell us about monotonicity and the precision of program analysis. Right, all yours, Marco.
Okay. Can you hear me? Yes. Okay. Thank you for the introduction. I'm Marco Campion at Inria. I'm a postdoc. This is a joint work with Caterina Urban from Inria and Mila Dalla Preda from University of Verona and Roberto Giacobazzi from University of Arizona. Okay, so I'll just start with a bit of context. We want to verify whether a program satisfies a specification using a sound program analysis. So in case so we designed our sound program analysis, and in case the analysis returned yes, then we know that the specification is satisfied. Otherwise, it may return an alarm. Sorry. The problem here is that we actually, in general, don't know if every alarm is actually a true alarm. So it may be a false alarm. This is due to the famous Rice theorem. So unless we are analyzing a trivial specification, we need to deal somehow with the false alarms. And so what people do usually in program analysis is try to modify or tune the program analysis in order to decrease the number of false alarms. And there are also like applications, real applications where the false alarms are critical. So we try to completely remove false alarm to get a very precise, a complete program analysis in this case. What we want to answer in this work is the following. We want to try to partially answer a question, which is, can we formally prove the existence of a program analysis over a program and a specification for which we are sure that there will not be false alarms, but just true alarms in this case. So can we prove the existence of this program analysis? And can we extend also this reasoning on maybe a class of programs, depending on their behavior, and a class of specifications? So we want to give a partial answer on these questions by considering program analysis, in this case, formalized by abstract interpretation. So in one slide, what is abstract interpretation? So we have our concrete operator computing over concrete properties, which may be undecidable. So the idea of abstract interpretation, the key idea is to replace the concrete computation with an abstract computation over decidable properties in order to be able to prove properties of program in this case. So for our purposes, we are going to consider a deterministic while language that we want to analyze. We are focusing on analyzing the output of a program and the numerical properties in this case. So we are considered as a concrete semantics, a standard collecting the denotational semantics. And then we are going to consider an abstract semantics, sound by assumption, over an abstract domain. And we are assuming that between our concrete set of concrete properties and set of abstract properties, we are assuming a Galois connection. So with an abstraction and a concretization function. So what does it mean soundness in this case? So here we have in the top corner, we have the inequality. So it means that the result of our abstract interpreter must be an over-approximation of the abstraction of the result of our concrete execution, which implies that if we want to verify a specification, so given a specification which is representable in our abstract domain, and we want to verify the concrete execution of a program over an input, if it satisfies that safety specification in this case, then we can we can use our abstract interpreter to verify this inequality. And if this equality is satisfied, then we can, for sure, thanks by the soundness assumption, we can conclude, yes, the specification is satisfied. We have incompleteness when we have a strict inequality in this case. So it might happen that our program analysis returns no on the specification, but in this case we may have false alarms because of the over-approximation induced by the program analysis. So the best scenario is when we have completeness, so when we have an equality in this case. So this means that even if our program analysis returns no, it is not satisfied, if we have completeness, then we are also sure that the actual raised alarm is a true alarm. So the specification, so the actual behavior of our program over the input does not satisfy the specification. So as you can see here, completeness is a very important property in program analysis. But of course, the problem is that it is very hard or even impossible to achieve. So it has been extensively proved in other papers that only trivial abstractions actually are complete for all programs. So it's impossible to build a program analysis which is complete for all programs and input. And we can also build, for every program analyzer, we can also construct, so build, implement a program whose analysis result is incomplete. So in this work, what we try to do in this case is to try to classify, so identify a class of specifications, so a class of abstractions, and a class of programs, and a class of inputs, for which, when we want to answer these questions on the behavior of the program, then we can formally prove the existence of an abstract interpreter, so of a program analysis over the abstract domains, over these abstract domains on this class, for which actually we have completeness. So all raised alarms are actually true alarms. And when this property is satisfied, we will say that the program P is complete analyzable for the abstract domain A at input I. So we can answer with only either yes or false or alarms, which are true alarms, on the specification, which are representable in the abstract domain A. So I'm going to show that here the monotonicity property over programs will play a central role. So in one slide, I try to resume the main result of the paper. So what is program monotonicity? When a program is monotone. So I will define monotonicity as given for all possible comparable inputs, we have that the result of the program on the inputs maintains the order. So the program preserves the order of the inputs, or for all comparable inputs, the program reverses the order of the inputs. So it is either non-decreasing or non-increasing. So the main theorem here is that whenever we are considering bounded inputs, namely inputs which have always minimum and maximum elements, and abstractions which are non-relational and able to represent intervals, so for example in two-dimensional rectangles, and the output of our program analysis is actually convex on the program, then I can show you that whenever the program is monotone on the over-approximation of the input, if we can prove the monotonicity of the program on the over-approximation of the input, then we are sure that there exists a program analysis which is complete for this abstraction and this input. So we can prove all the specification representable in the abstract domain without the false alarms. This is our main contribution. So, for example, let's consider the ReLU activation function in neural networks, which is a very simple program, returns 0 in case of negative numbers, otherwise the identity. We can see that, for example, this program is non-decreasing, so it is monotone, in this case for all possible inputs. And so thanks to our theorem, if we want to analyze the output of this program on the interval abstract domain, then we are sure that there exists actually an abstract interpreter that can answer, that is precise, which is complete. So in this case, I can also build the actual abstract interpreter, and I can show that this analyzer is actually complete for all inputs in this case. So we can prove all the interval specification on the output of this program. And we can, for example, go on like considering other activation functions which are non-decreasing, and we can conclude again which with these programs are actually complete analyzable for the interval subdomain. And so, for example, since monotonicity is closed by composition, so if we are composing non-decreasing activation functions with non-decreasing nodes by obtaining a non-decreasing neural network, in this case, then again, we can conclude that the output of our non-decreasing neural network is complete analyzable for intervals, for bounded inputs in this case. So what we want to do now is try to, okay, so we have a program, we have a set of variables, but maybe we are not interested in all the variables of the program, so maybe we just want to analyze a subset of the program variables. So in this case, we define what is V monotonicity. So we specify monotonicity over a set of variable V, in this case. And so we just consider the comparison between states only on the set of variables V. And we say that program P is V monotone for the set V at an input I whenever the program is V non-decreasing or V non-increasing at I. So the next question is, okay, but can we verify V monotonicity of programs? Well, we define a proof system, a sound proof system in this case, compositional on the program syntax. So we want to try to verify the predicate, this predicate, which is monotonicity over a program P, an input I, and a set of variable V. So this predicate will be true whenever the program is non-decreasing or non-decreasing over the input I for the variables V. And we are going to focus on the non-decreasing property in this case, since the non-increasing property is actually dual. So this is the set of rules of our proof system, and since I don't have enough time, I'm going to show you just the branch rule in this case to prove monotonicity for the branch rule. So the idea here for proving monotonicity of the non-decreasing property of a program with an if branch, which is actually the main program which may cause the, which may break the relation, the monotonicity relation over states. Then here the idea is as, okay, let's consider that the branches at least are monotone, so are non-decreasing, sorry. If the branches are non-decreasing, then here we are, in order to prove monotonicity of the branch, of the if branch in this case, well, we can consider boundary states. Whenever we have a positive linear guard, which means that it divides the input in two spaces, then we can consider only boundary states. So we can try to verify the non-decreasing property only on the states which are exactly on the guards, and try to see, and if the states actually in the program, the two branches satisfy the non-decreasing property on the guards, on the boundary states, then we can conclude that the program, the if branch in this case, is non-decreasing. So, for example, again, why we can prove the non-decreasing property of the ReLU program, because the two branches are non-decreasing, and so here the boundary state is just 0. The guard equals 0 in this case, and so we can conclude that the program is the ReLU program is non-decreasing. So by concluding, this is the specialized theorem for programs with a set of variables V. So whenever we specialize also the property of boundness and convexity. So whenever we have a bounded input on the set of variables V, a non-relation upstart domain able to represent intervals, and a convex result on the variables V, then whenever the program is V monotone, we can conclude that the program is also V complete analyzable for the upstart domain A. So the actual proof here is just that, so I don't have enough time to show the complete proof, but the idea is that why it is possible to build a complete program analysis because we prove actually that the best correct approximation is complete. So every spurious element added by the abstraction is actually somehow considered by the program and does not generate false alarms in this case. And so we have the P is actually complete analyzable. So by concluding, so we have shown that the precision in program analysis is influenced by not only by how programs are written, so by the syntax, but also what programs compute. For example, all monotone functions, we proved actually that all monotone functions, we can build a program analyzer for monotone functions and for example, some inputs and some abstract domains. So the key idea here is to try to maybe if you want to, for example, prove specification over intervals, we can maybe identify monotone components on our program for which we are sure that we can precisely analyze those components. And maybe a question could be, can we classify an extensional class of programs for which, with respect to a given program analysis, which is for which our program analysis is actually complete? And this ends my talk. Thank you.
Questions for Marco?
Okay, I have a question about the analysis that comes out of this. So you say that a complete analysis exists. Can you say something about whether it runs very fast or it's very slow or it's computable or just some properties of it?
Okay, so it is computable, but actually since we proved the completeness of the best correct approximation, so we actually proved the existence, but we are not actually proved the existence of actual an always terminating program. So the theorem here is that if you want to build actually in actual a complete program analysis, then whenever your program analysis is complete, then also the best correct approximation is complete. So in order to be able to actually consider to be able to precisely prove a program, the first step is to prove that your best correct approximation is complete. And then you are sure that, I mean, it could exist or not an always terminating, but there is the possibility to build a precise program analysis. This is the first step.
Another over here.
Hey, I'm worried I might just wind up asking the same question again. So you can just go, I've already answered that. But thanks for the talk. What does this assume about the widening operators?
Okay, so we are not considering here widening because we are actually defined that, so we didn't, the proof here of the theorem is not an actual program. So it is that the function is actually, you can build the function over the abstract domain which is complete. Then the next step will be to, of course, to find an always terminating program. But we actually prove that the best correct approximation function over the abstract domain is complete, which is not an actual real program analyzer because it is not always terminating. But in order to build a program analyzer always terminating complete, you have to be able to prove that the best correct approximation is actually complete. So it is not possible to have an always terminating program analysis complete, but the best correct approximation is not complete because you have to always satisfy this inequality. So every program analyzer is actually at least as precise as the best correct approximation.
Cool, thank you.
A question here. So I'm wondering how many kinds of examples you have of programs and monotone, V monotone, and abstract domains that actually satisfy your property. So you said ReLU was one, but I presume affine transformations will not be because of, I don't see how it can be. But
yeah, of course.
And so are there? Can you give us some examples of where your restrictions will be met except ReLU?
Well, you can also, I mean, A program as a whole might not be monotone in this case, but you can also, what we try to do with our proof system is try to maybe identify variables that behaves monotonically. So for example, I don't know, counters variable, many counters variable behaves monotone, so you can maybe identify the variables and you are able to prove, in this case, precisely some properties over, for example, intervals.
Okay, we can do one very quick question.
And there is that side. Oh. Sorry.
What I have not understood is P, because do you take the analyzer, the relation between the analyzer and P? Is it for one program you get one analyzer, or for a infinite set of programs you get the same analyzer?
For one program, you get an analyzer.
Oh.
Yes. Well, but it's not an actual real implementation, actually.
Okay.
Okay, thank you again, Marco.